All right, hi everyone. I'm Maple Ong. I'm part of the program committee this year. Who here loves flaky tests? Yes! I'm so glad. Thank you. So you're in the right place. Um, Introducing Alan Ridlehoover. I'm gonna read a bio. I should have had this open. Alan is a passionate software engineer who loves Ruby. He is an empathetic leader at Cisco Meraki, a fallible human, and a man of several hats. Welcome, Alan.
It's after 4 o'clock. That release was due an hour ago. You've got less than an hour to leave, or you're going to be late to that thing. You can feel the clock ticking. Slack clicks to life. You check your messages. The build failed again. You look at the build, you look at the clock. You do not have time for flakiness. So you rerun the build. Again, 2 builds in, 5 failing specs. None of them have anything to do with your commit. All you can think about is how you cannot be late to another thing. If only you knew the secret ingredient that all flaky tests have in common. You might be on your way to that thing right now. Hello, my name is Alan. I am an engineering manager at Cisco Meraki, probably the largest rail shop you've never heard of. And though I'm not a baker, I do know a thing or two about flakiness. In fact, sometimes it's all I can think about. Seriously, since I started automating tests over 20 years ago, I have written my fair share of flaky specs. Daylight saving time is my personal nemesis. I can't tell you how many times I've tripped on it. Let's just say I'm well into the shame on me part of that relationship. Or I was, but I'm getting ahead of myself. Let's start with a definition. What is a flaky test? Well, a flaky spec is one that changes without modification to either the test itself or the code being tested. So if you write a spec A, and a method foo, and it passes, then you should expect that as long as A and foo don't change, it should continue to pass. If A and foo stay the same, but the outcome changes, that's when you know you have a flaky spec. But how does this happen? Well, it happens because of that secret ingredient that I mentioned. All flaky tests have it in common, but what is it? What is the secret ingredient? It's an assumption. All flaky tests make invalid assumptions about their environment. They assume their environment will be in a particular state when the test begins, but that assumption is rendered incorrect by some change in the environment or between or during test runs. Okay. What causes that change to the environment? Well, there are 3 recipes. The first is non-determinism. The second is order dependence. The third is race conditions. Let's take a look at each one of these along with some examples in code, starting with non-determinism. So what is that? What is non-determinism? In fact, for that matter, what is determinism? Well, a deterministic algorithm is one that, given the same input, will always produce the same output. So for example, if I take these parameters, I pass them to a method called add, they should always return 2, no matter how many times I call that method. But what if there were a method foo that always returned true until it didn't? That's the definition of non-determinism. An algorithm that, given the same inputs, does not always produce the same outputs. Well, how could that be? Well, it might sound obvious, but if you're utilizing a non-deterministic feature of the environment or the system, then you are going to be producing non-deterministic code. So the trick is, how do you make non-deterministic tests? So here's some ways that you can that non-determinism will sneak into your code. You can use random numbers, which obviously are intended to be random. You can use the system clock, my nemesis. You can use a network connection. Sometimes they're up, sometimes they go down. So the tests might pass or fail. And there's floating points as well. Precision on floating points isn't guaranteed, so a test might pass once and then fail the next time. And these are just a few examples. I'm sure this list is not exhaustive, but what if our code relies on these things? How do we make the tests deterministic? The trick is to try and remove the non-determinism by mocking it or stubbing it, or to account for it by using some advanced RSpec matchers. To do that, you can stub that random number generator to produce a specific number. You can mock or freeze time. You can stub the network connection to return a specific response. And for floats, you can use a couple of RSpec's advanced matchers like be within or be between instead of using an exact match. And finally, please, whatever you do, do not forget to document that undocumented thing that caused the test to fail. So in my case, make sure I write the test after daylight savings time to prove that it still works. All right, so while that build is running that we started at the beginning of the talk, let's see if we can fix some of those flaky specs. We don't want to be late for the thing after all. So first, a bit of context. This code that I'm about to share is entirely made up. Well, technically, I guess all code is made up. But what I mean is that this code was made up fresh just for this talk by me with TDD, not ChatGPT. It's not production code, but it is code that I've seen in production applications. It's a bit of a hodgepodge. It's a class called RubyConf that provides a few methods that the organizers might find helpful. Okay, so here is a method to determine whether or not the conference is currently in progress. I'll let you take a look at that for a sec. Notice that the method is using the system clock, and I realize now after watching Joelle's talk that I'm using the wrong date time. But simple enough, right? Let's look at the specs for this. Well, there's only one. Okay, let's look at that spec. It says that the in-progress method returns false before the conference begins. Now that seems like maybe the author forgot a couple of use cases. But this is actually something common that I see with date-based specs. The author of the spec is living in the now. They're not thinking about the future, kind of like me with daylight savings. And we forget. We forget to write that spec that goes along with whatever happens after the clock changes. So I'll bet that this spec was passing before the conference, but now that the conference is happening, it's probably failing. So let's play with the system clock and see if we can't figure that out. All right, so as I predicted, it passed if I set the clock back in time to October, well before the conference. Not at all the day that I wrote the slide. So we know this is a flaky test now because it was running and now it's not. So if I set the clock forward to the beginning of the conference, it fails. So how do we fix it? Well, remember, this is a non-deterministic issue. We need to either mock or account for that non-determinism. And so what I'm going to do in this case is I'm going to freeze time. Now here's the code and the spec as they were before. and here's the difference. So this is the fixed spec, and you'll notice only the bottom half of the screen is changing. The code's fine. The code has no problems with the code. This is only a problem in the spec. And what it's doing is it's freezing time. So it's setting the time to a specific date in this block. And so the code will only, in this block, will only execute under that context. As soon as the block ends, the system is sent back to its normal state. Okay, let's see if that fixed it. All right, so November 13th, the spec is now passing. In fact, I even went back and I added those other specs that were missing, the one for before and the one for after and during. Those look like this, and you'll notice they're just doing the exact same thing. They have the different date and a different outcome, but they're basically the same test. All right, so we fixed one of those flaky tests. Let's take a look at another one. This one is about a network connection that goes down. So it's not uncommon for your code to need to talk to another service across a network. In this session description method, we're calling an API endpoint to fetch the conference schedule, and then we're parsing it, finding the session that matches the title parameter, and returning a description. Now here's the spec. I know that's a lot of code to take in, so I'm going to take a sec. All right. So, with Wi-Fi enabled, this spec passes. Note that the call to the well, it might not pass here at the conference, but it does pass in this scenario. And it adds over a second to the runtime, as you can see there. And that's when it succeeds. A lot of times, HTTP calls, when they fail, they like take 60 seconds to time out. So that makes it a lot harder to make these tests useful. Plus, when I turn off Wi-Fi, the spec fails. So fortunately, it fails quickly because the network failure is on my end, not the server end. But these are particularly nasty tests to debug because that loss in connectivity is not logged or persistent. So by the time you get around to debugging the failure, it might not be possible to reproduce without turning off your Wi-Fi. So pay attention to HTTP calls in your code or any other type of call that crosses a network like a gRPC or something like that, and try running the specs with Wi-Fi turned off. You'd be surprised how many things you catch that way. Okay, let's fix this thing. Here it is, same exact code, same test as before, smaller font size. I'm not going to put as much code on the screen as Jeremy just did, but here we go. That's the fix. Now, note again, the code at the top half of the screen is not changing. Whoops, not changing because this fix is in the test. Most of the changes to the test are just setting up that stub for the network response. That's these lines of code here. This allows the spec to validate that we're parsing the results correctly. And that's really the code we care about. We don't actually care whether the external service is up and running when our specs are running. It shouldn't matter. And on that point, I often get pushback. Folks will ask me, well, what if the API changes? How are we going to know if the spec isn't going to fail because it's mocking the result? And my answer to that is that every spec should have one and only one reason to exist. Now, in this case, that reason to exist is to verify the code that we wrote works as we expect. It's a unit test. And we want these to have as few dependencies as possible so that they'll execute quickly. Now, you may also require a spec to validate that an API schema hasn't changed. That is a different reason for a spec to exist. It is not this spec. In fact, it's not even a unit test, it's an integration test. And because of that, it's even an integration test that's designed to fail. We want it to fail when that schema changes. So it's not something we want to run alongside all of our unit tests, which are designed to pass every time. So maybe the integration tests should be run separately on a schedule instead of amongst all of our unit tests that we run on every build. All right, let's run the spec and see if it passes. Sure enough, if I turn the Wi-Fi off, the spec still passes now because I'm mocking or stubbing the response to the network call. It's also important to point out the difference in execution speed here. The live version, if you'll recall, took 1.3 seconds. This one took 1/100th of a second. And that can become incredibly important as your test suite grows, particularly when it hits 100,000 specs like we just did. All right, it is 15 minutes in, and those specs took us about 10 minutes to fix. That wasn't so bad. Let's see if we can solve some more of these before you have to head out. All right, let's take a look at order dependence next, starting with a definition. So order dependent specs are specs that pass in isolation but fail when run with other specs in a specific order. So for example, if both test A and test B pass when run in alphabetical order, but test A fails when run after test B, that makes test A flaky and test B leaky. But what does that mean, leaky? Remember, these specs are what? They're making an invalid assumption about the environment. And that environment includes all the shared state that they have access to. It works kind of like this. Let's pretend this blue square is the starting point for the shared environment. Spec A runs, it gets the blue square, and it passes. Spec A does not change the state, so Spec B runs in the same context, it also passes. Now, let's imagine that running them in the opposite order, where Spec B gets the starting environment, gets the blue square, but adds or changes some state, turning it into a pink hexagon. So now, this state is what test A is going to run in. It didn't expect that, so it's going to fail. So basically what happened is Spec B leaked some state, either deleted or added or changed something that's in the environment, and causing Spec A to fail. Now, Spec A was only failing because it was susceptible to that. It made that invalid assumption about its environment. For this reason, we think of these tests as, they're often referred to as leaky tests. And isn't leakiness the problem here? Like, isn't Spec B the problem? Well, actually, no. They're both to blame. And the reason is that they have, one is leaking and the other one is susceptible to it. So only one of them, though, is breaking your build, which means that you should focus on that one first. Now, often you'll find that if you fix the broken spec, it'll point to a broader solution that will solve the leakiness as well. But how do you do that? How do you fix these order-dependent flakiness tests? Well, first, let's take a look at what causes this kind of failure. Order-dependent failures are caused by mutable state that is shared across specs. This could be in the form of broadly scoped variables, like a global or a class variable. It could be a database, it could be key value store, a cache, or even the DOM if you're writing JavaScript specs. So that's what causes it, but how do you reproduce these things? Well, the first thing to do is to eliminate non-determinism. Make sure it's not non-deterministic. And you can do that by repeatedly running the same spec in isolation. Now, it might take a while, but eventually, if it's non-determinism, it will fail. Now, if you can't reproduce it that way, then what you want to do is you run all the specs that ran together with this spec, probably from a process on the build server, locally, and run them in random order, and continue running them in random order until one of them fails. Now, if the default order doesn't solve it, you can run rspec order random to get into the random order. Keep running them that way until you find a seed that consistently causes the failure. Then the next thing you want to do is locate the leaky spec or specs. Now, I say specs, plural, but it's possible that it takes multiple specs modifying the environment before the failure will reoccur. So keep running it until you find that seed that causes the failure. And then once you've found it, you can use RSpec bisect, which is another feature of RSpec, to find the actual leaky specs for you. And I'll show you how to do that in a minute. First though, what is it we need to do to fix these things once we've found them? So you can remove the shared state. You can make it immutable, or you can isolate it. So don't use those broadly scoped variables. They're a recipe for flakiness. Mock shared data stores which you can do easily with the layer of abstraction. Typically, you might see the repository pattern used here. You can use database transactions, which if you've used database cleaner, that's what you're doing. Or you can reset the shared state in between specs. All right, let's see if we can solve another one of those flaky specs that's keeping you here, keeping you away from that thing, by looking at a shared state example. So here, we have a simple getter and setter to store a favorite session. Notice that both the getter and setter leverage an object called cache, and they call a method on it called instance. What is that? Let's take a look. So the cache is a simple in-memory key-value pair backed by a hash. And the instance method is effectively turning it into a singleton, so that every reference to the cache.instance method is returning the same instance. Now, here are the specs for the favorite session getter and setter. Now these specs pass when run in this order: getter first, then setter. But they'll fail in the opposite order because we're storing the title of the session in the cache. So if we run the setter first, we're going to set the cache. And then the getter will return the value in the cache instead of the default value, whereas the spec for the getter is looking for that default value. Now to prove that, let's run this with RSpec in order random mode and see if we can't reproduce the failure. So here you can see I ran the spec with order random, and RSpec produced a random seed, 12322. The getter ran before the setter with that seed, so it passed. Let's try again. Okay, so here I'm still running with order random, but RSpec chose a different seed, 63603, and lo and behold, the setter ran first, so the getter failed. So how do we go about fixing it now that we know? Well, we know actually only that one of these three specs caused the failure. They all ran before before the getter spec, so any one of them could have been the problem. Now, we have a suspect. We think it's the setter, but how do we know for sure? Now, this is where RSpec bisect comes in. So let's take a look. Here, I'm running RSpec bisect with the same order random clause with the same seed that produced the failure. Now, this is important because bisect won't work if you hand it a command that won't fail. So I had to find the seed that caused the failure first. The first thing bisect then does is it tries to reproduce the failure, because if it can't, it'll just exit and say, I can't help you. Whoops. Next, it analyzes whether or not that failure appears to be order dependent. And in this case, it does. You can see failure appears to be order dependent. So it performs a binary search, looking for the spec or specs that need to be run first in order for the failure to happen. Now, note that this can take a very long time if that list of candidate specs is long. So finally, if it finds a reproducible order in which the test fails, it will give you the command to run to get that failure to reproduce and cause it to just be the specs that are necessary. So if you run that command like this, you can see here I'm running exactly the command that it proposed, including order random. I added format documentation here so we'd see the names of the tests. And sure enough, the setter is the suspect. We now know that's the test we need to go arrest. So how do we fix it? Well, here we are back at the beginning. Again, font's a little smaller so I can add the solution. One way we could approach this would be to add a clear method to the cache and call that method in between specs. But because our specs are currently sharing state, if we ran them on the build server and we were clearing the cache in between specs, running them in parallel, what would happen? We'd have a race condition. And most likely that one test would interfere with the execution of another. So what I prefer in this situation is to use a technique called dependency injection. Now, it's a simple technique with a weird sounding name that all it does, we're going to pass the cache object into the RubyConf object when we create it. So each spec will be able to pass its own cache into the RubyConf object. Now here's what that looks like in code, starting with the actual implementation. So first, here's the new initializer. Notice that the cache parameter defaults to cache.instance. Now, this way, if we don't pass anything when we're creating the RubyConf object, it'll just use the singleton, which is exactly what we want in production. Now, by doing this, though, we've created a seam in the software that allows the specs to use their own cache objects. Now, this prevents state from leaking between the specs without modifying the behavior of the production code. All right, let's now look at the specs. So, here we are creating a new instance of the cache class and passing it to the RubyConf object when we create it. And that's it. That's all there is to dependency injection. You create a parameter in the initializer, you hand the object to the collaborator. Okay, let's run the specs again. So now I'm running the specs with the same randomized key or seed that caused them to fail in the first place. And now they pass even though the setter ran before the getter. Voila. Okay, we're making good progress. It's only 4:30. You might actually make that thing after all. So let's take a look at a couple of more broken specs. But first, let's talk about race conditions. So what is it? What is a race condition? A race condition is what can happen when two or more parallel processes are competing over the same scarce shared resource. Now, let's look at how that can happen with a file. So first, let's look at two specs running in sequence to see how they work when writing to a file. The first spec is going to write to the file, read from the file, check the result, and it'll pass. Now the second spec is going to write to the file 2 times, read from the file, and pass. But if I run them in parallel, first spec 1 writes to the file, then spec 2 writes to the file, then spec 1 reads, checks the result, and fails because there are 2 records when it only expected 1. Next, the second spec writes again, it reads, and it fails because there are now 3 records when it only expected 2. So, in this case, both specs are susceptible to parallel flakiness due to a race condition. Of course, this is asynchronous code, so who knows? It might actually pass. And that's why race conditions are so notoriously hard to reproduce. So how do we go out debugging them if we can't reproduce them? Well, you want to take a methodical approach like we did with the order-dependent specs. The first thing is to try and eliminate non-determinism. Run that spec that's failing in isolation repeatedly, and if it fails, then you know that's non-determinism. And if not, try to eliminate order dependence. Run it repeatedly with the specs that it failed with on the build server in different orders. Now, if you can reproduce the failure that way, that's an order-dependent problem. You can use bisect to help you there. Finally, if that doesn't work, run the specs repeatedly in parallel with the parallel RSpec gem. I mentioned this gem specifically because other gems that help you with this seem targeted, like parallel test or knapsack, seem targeted at running Rails apps on their CI server. So it's best if you can debug this stuff locally, and parallel RSpec will let you do that. If you still can't reproduce it, try adding order random to the parallel RSpec, and it will give you the same parallel system, but it'll randomize the order the specs are in. So, once you have reproduced it, or even if you can't, what are you going to look for to try and fix these things? Well, the main cause, remember, is that race conditions are they're caused on the build server usually by asynchronous code competing for shared resources. And those things might include things like the file we just looked at. There could be a socket, could be a thread pool or a connection pool, or even memory. Once you have a suspect, once you know one of the things that it could be, how do you fix it? Well, there's a lot of different ways. Depends on the situation. So if it's an IO-based issue, you can use a class called string IO as a stand-in for the other type of IO that you're actually trying to perform. If it's a thread issue, you can try writing thread-safe code. Oh, sorry, missed one. You can test that messages are passed correctly and not test the results coming out of the object. Then, if it's threads, you can write thread-safe code. Of course, you could also extract that code out of the threaded class into a PORO that you call from the thread, and then test the PORO synchronously, and trust that Ruby knows how to instantiate a thread and run code on a thread. You can also switch to fibers instead of using threads. Now, fibers are super cool, because, sorry, I'm moving the wrong direction. Too many animations. Okay, back to the right slide. Here we go. I already talked this one. Fibers are super cool. The reason fibers are so cool is that you can test them synchronously. You don't need to test them on a thread. And they also make it incredibly hard to create a race condition, because one of the things they do is they take control of the CPU and they don't hand it back until they're done. So any kind of atomic operation that you need to perform that is several commands, you can do that without having to account for thread safety, where the CPU is sucking or the OS is taking the CPU away from you. So let's take a look at how to fix one of these things. Now, these are the last two Flaky specs that are actually keeping you here, so let's take a look. All right, so this is a feature of the app that manages a list of reservations. Now, there are two methods, one to reserve a seat, the other to get a list of attendees. And you can see that reserving the seat just writes to a file, and getting the attendees back is just reading from that file. So let's take a look at the specs. All right, so the first spec ensures that writing Mickey Mouse to the file grows the number of attendees by 1. The second spec ensures that when writing multiple lines, Donald and Goofy, the attendee count goes up accordingly. So, when I run them in sequence, they pass. In fact, they'll even run in sequence if I switch the order. But if I run them with parallel RSpec, they will fail. In fact, both of them fail. In this case, the second spec actually failed first because of parallelism. And the attendee count actually grew by 3, not 2, like I showed a minute ago. And the first spec actually finished second, and it failed because the record count grew by 2, not 1. So we've already seen how that can happen, but let's walk through it again a little slower. before we get into that, let's look at how this RSpec code works. It's not as simple as most RSpec tests. So here's the expectation for the second test. It has 2 blocks of code. The first is passed into an expect method. The second is passed into the change method. Now, when RSpec executes, it's going to run this block of code first. That is, it's going to check the attendee count before it runs the actual test. Next, it's going to run the expectation block, and then it's going to run this block of code again to get the final count of records. So, and then it'll check the delta between the initial and the final and compare that to whatever got passed into by, in this case 2. All right, so now that we know how RSpec is going to do this, let's watch how this spec actually executes. So first thing that happens is the second spec reads the file. It finds that there are 0 records. Next, the first write in the second spec executes. So now Donald is in the file. Next, the first spec checks its initial value. It finds a value of 1 record in the file. And now both of the other writes happen. Now, it doesn't matter what order they happen in. We could check the file if we really cared, but they both happen. Then both reads happen. We happen to know here that the second one happens first because that's the test that was in the output first. But it's going to look at what value was in the file, how many records. Both of these are going to see 3 in this case. Now, the delta between 0 and 3 is 3. The delta between 1 and 3 is 2. And neither of those match the by clause, so both tests fail. All right. So now we know how it failed. Let's go back to the beginning and show you the solution. It turns out the Ruby core team actually thought of this. Bless their hearts. They knew that testing asynchronous I/O was going to be really hard. So they included a class called string I/O in order to simulate other kinds of I/O in specs. String I/O is a string, but with the interface of a file. So what we want to do is we want to allow file to receive open and yield a string I/O object. Now what that does is that it means that now when I call file open, the actual object that it will receive is a string I/O object. Now, one caveat here, it works just like a file. So this code is going to work just fine. One caveat with the string I/O is that you need to rewind it before you can read it. The reason for that is it's a file, essentially. The reason we didn't have to do that previously was the file open was a block, and as soon as that block ended, the file fell out of scope, and it was closed automatically for us. Because we are defining this string I/O class in the test, using it in the code, it doesn't fall out of scope until the test ends. So we need to rewind it before we can read. All right, proof is in the pudding. Let's see if we fix this race condition. All right, we got it. Parallel RSpec proves they're both passing now. Okay, here we are, 37 minutes into this talk, and we found all of the flakiness and we resolved all of it. So it's time to wrap things up real quick so we can get to that thing in the lunchroom. Because I don't know about you, but this test always makes me hungry. Okay, here's a cheat sheet for the entire talk. First, non-deterministic flakiness reproduces in isolation. Look for interactions with non-deterministic elements of the environment. To fix this kind of flakiness, mock the non-determinism to make it deterministic. Don't forget about time comp when working with date and time-related specs. And there are tools like WebMock and VCR for handling specs that require network connections. But I prefer to use RSpec like I did earlier. So there are plenty of folks who find these tools useful. I thought I'd mention them. Next, order-dependent flakiness only reproduces with other specs when run in a certain order. Now, because of that, they will not reproduce in isolation. Look for state that is shared across tests. and to fix order dependency, remove the shared state, make it immutable, or isolate it. RSpec order random can help you here by reproducing the failures, and RSpec bisect can help you by locating the leaky spec that's causing the failure. Finally, race conditions only reproduce with other specs when run in parallel, not in isolation. Look for asynchronous code or exhaustible shared resources. And to fix race conditions, isolate things from one another like we did with string I/O, or use fibers instead of threads. I mean, seriously, these things are amazing. You got to try them. Finally, you can use parallel RSpec to reproduce the failures locally instead of on your build server. Now, keep in mind that original point. All of these specs have a common problem. They're making an invalid assumption about the environment in which they're running. And sometimes just remembering that fact will help you identify and resolve the flakiness. Ask yourself, how can I ensure that this spec has the environment that it expects? And one more thing. I have a bit of a hot take here. Debugging this stuff is incredibly hard, but it gets 1,000 times harder if your specs are too dry. So avoid using these features of RSpec. They seem harmless at first, even useful when you're writing the specs, but ultimately they're going to make debugging way too hard. So avoid shared specs, avoid shared contexts, avoid nested contexts, and avoid let. Your specs should be incredibly communicative. They are, after all, the executable documentation for your code. If you have to scroll all over the place or open a ton of files to find and debug, to create the code in the first place, then you can be guaranteed you're going to be doing that when you're trying to debug it later when it's failed, probably at 2 a.m. when you're trying to get the release out. So, keep your tests wet. I'm not the only one who says this. The fine folks at Thoughtbot agree. They have written several articles on this. And in fact, I honestly think that dry might be the worst programming advice ever. You can go read what I have to say about it there. I told you it was a hot take, but it sounds like I have some agreement here, so that's awesome. If you still disagree, come find me at lunch. I want to change your mind. Again, my name is Alan Ridlehoover. I do know a thing or two about flakiness, but it took me over 20 years to get here. I hope this talk has short-circuited that for some of you. As I mentioned at the beginning of the talk, I work for Cisco Meraki, so I also know a thing or two about connectivity. Here's how to connect with me. And that last item there is the source code for this talk, including the fixed code, but it's tagged, so you can walk through it one thing at a time. So you can look at the failure, and you can look at the success, or you can practice fixing the failures. Cisco Meraki is probably the largest Rails shop you've never heard of, and we are growing. So if you're interested, there are a limited number of roles open right now. Come chat with us at the job fair and find out what it's like to work at Meraki. Finally, a tiny bit of shameless self-promotion. I love Ruby so much that my friend Fido and I often write code on the weekends just to release something into the wild in the hopes that somebody will find it useful. You can find links to our stuff at firsttry.software, including Rubyist, which is an opinionated VS Code theme. It's the one you saw in the talk. So if you liked it, we'd love for you to check it out. Thank you so much for coming. If you have any questions, I'll be off stage.